Welcome to Everyday Explained, your daily 20-minute dive into the fascinating hows and whys of the world around you. I'm your host, Chris, and I'm excited to help you discover something new. Let's get started.
You walk into a room, flip a switch, and bam, the lights come on. You plug in your laptop, it just charges.
Yeah.
It seems so simple.
Deceptively simple.
But behind that, there's this absolutely incredible journey that electricity takes. I mean, a journey across huge distances through what some people actually call the most complex machine ever built.
It really is mind-bending when you think about it. We're interacting with this unbelievably intricate network probably thousands of times a day without even noticing.
Right.
Imagine like a system of wires and connections, maybe more complex than, I don't know, more wires than a million spiders could weave together. And it constantly needs balancing and adjusting. It's wild.
And our mission today really is to follow that energy.
Yeah.
From where it's, born all the way to your wall outlet. You've given us this stack of sources, articles, diagrams, explanations that seem to provide all the pieces of this massive puzzle.
Yeah, looking at all that info together can feel a bit overwhelming at first, no doubt. But our goal here is to cut through that, distill the really key insights and bring you the surprising bits you might not know. Keep it engaging, maybe even a little fun along the way.
Absolutely. So we're going to trace the flow of that power, starting with the really big picture.
Right, because the electric grid isn't just like one single thing everywhere. Our sources explain it's this massive interconnected network. You've got generation plants, transmission lines, distribution systems, all this infrastructure stretching across huge areas.
Like different grids almost?
Kind of. In North America, it's often divided into major interconnections like the Eastern, the Western, and ERCOT down in Texas. They mostly operate independently, but they still need to stay coordinated.
Okay. So let's start right at the beginning then. The supply chain generation.
Yeah.
This is where electricity actually gets made.
Think of power plants as the sort of industrial heart of the grid, the factories, basically, where raw energy gets turned into usable electricity.
And the sources mention a whole bunch of ways they do this, right? Different fuels.
Oh, yeah. Wide variety. Natural gas is huge. Solar, wind, nuclear energy, coal, still, hydro, that's hydropower from dams, and even geothermal, using heat from the earth itself.
And the basic idea, for most of them anyway, is turning some other kind of energy into electrical energy. Often it involves spinning something,
Exactly, spinning a turbine. You might boil water using coal or gas or nuclear heat to make steam. That steam spins a turbine, which is connected to a generator. Or, wind turns the big blades, water flows through dams, turbines. It's mostly about getting that rotation.
Mostly. But not always.
Right. Solar is the big exception, our sources point out. Photovoltaics, they call it. You use sunlight to directly excite electrons in materials like silicon. No moving parts needed there, which is, a fundamentally different way of doing it.
Interesting. And it's not just what energy they use, but how these plants operate that matters for the grid.
Definitely. The sources talk about different types. You got your baseload plants. Think large nuclear reactors or big hydroelectric dams. They can take a while to start up, but once they're going, they run pretty much constantly. They provide that steady, reliable block of power day in, day out.
Okay, the foundation.
Then you have peaking plants, often fired by natural gas. These guys are designed to start up relatively quickly, maybe minutes, maybe a few hours. They're your dispatchable generators, ready to ramp up fast when demand suddenly spikes.
Like when everyone gets home on a hot day and cranks the AC.
Exactly that scenario. And then increasingly important are the intermittent sources, solar and wind.
Right, the renewables.
They're clean, getting cheaper, which is fantastic. But the challenge is they only generate power when the conditions are right, sun's shining, wind's blowing. And that's not always when we need the power most. That creates a balancing act for grid operators.
Which brings us to storage.
Precisely. Our sources really highlight the growing importance of energy storage. Things like huge grid-scale batteries or pumped hydro storage where they pump water uphill when there's excess power and let it flow back down through turbines later.
Ah, okay.
These let us capture that extra renewable energy when it's available and then discharge it back onto the grid during peak times or when the sun isn't shining. It's becoming absolutely essential for managing that supply and demand balance.
Okay, so we've generated the power, but it's often made miles and miles away from where people actually live and work. So it needs to travel.
And that's where transmission comes in. Think of these as the massive high-speed highways for electricity.
The really tall towers, the ones that look like, I don't know, giant metal trees or maybe huge Tinker Toy constructions. holding up those thick wires that stretch for miles.
Yep, those are the ones. They definitely change the landscape, but they're vital.
Why so big and tall?
Because they transport electricity at extremely high voltages. We're talking hundreds of thousands of volts. And the reason, our sources explain, is all about efficiency.
Higher voltage is more efficient. Seems weird.
It is a bit counterintuitive, yeah. But transmitting power at higher voltages drastically cuts down on energy loss over those long distances. Think of it like pushing water through a pipe. Higher pressure means less friction loss for the same amount of flow. So less electricity gets wasted as heat in the wires.
Wow. The sources had a cool stat on that, didn't they? Something about doubling the voltage cutting losses significantly.
Yeah, they mentioned that if you double the voltage, you can send the same amount of power with only a quarter of the energy loss, boost it 10 times, and the losses drop to like 1% of what they were.
Incredible.
That's why they use step-up transformers right at the power plants. They boost the voltage way, way up before sending it onto these transmission highways.
Okay, but you definitely can't plug your phone into hundreds of thousands of volts.
No, definitely not. That voltage is incredibly dangerous and totally unusable for homes or businesses. So the next phase is distribution.
Right. Getting off the superhighway and onto the local roads and neighborhood streets.
Exactly. Those high-voltage transmission lines connect to substations. You've probably seen them in enclosed areas, often with fences, lots of humming transformers and equipment inside.
The buzzing places.
Yeah, those. Think of them as major interchange points, or maybe voltage pit stops. They have step-down transformers that dramatically reduce the voltage from those super high transmission levels down to lower, but still pretty high, voltages suitable for local distribution.
And then from the substation.
Then distribution power lines take over. These are the lines you usually see running along streets, often on those familiar wooden poles. They carry the power from the substations throughout the community, getting it closer to where people actually need it.
But still not quite ready for my toaster.
Not quite yet. There's typically one final voltage step down needed.
And that happens right near my house usually. On the pole or in a box.
Exactly. Those smaller transformers, the ones that look like gray or maybe green metal buckets hanging near the top of power poles, or sometimes they're big green metal boxes sitting on the ground if the lines are buried underground.
Okay, I know those.
Those distribution transformers do that last crucial reduction. They take the voltage from the neighborhood lines and step it down again to the levels we actually use in our homes in North America. Typically 120 volts for most lights and outlets, and 240 volts for bigger appliances like electric stoves, dryers, or central air conditioners.
Now, something really interesting our sources mention is that these transformers used to be just one-way streets, right? Power flows in.
Traditionally, yes.
But now, with things like rooftop solar panels, what do they call them? DR?
Distributed energy resources.
If you have those and you're making more power than you're using at that moment, that extra power can actually flow backwards through that same transformer and onto the local grid.
That's right. It can go serve your neighbors. It's a really fundamental shift happening, enabled by smarter technology and changes in how the grid operates, moving towards a more decentralized two-way system.
Very cool.
But whether the power's coming or going, first, it has to physically get from that local transformer into your house.
Okay, so that brings us right up to the doorstep, getting the power inside.
From that transformer, whether it's on the pole or on the ground, you have what are called service wires connecting directly to your home. For a typical North American house, our sources explain this is usually 3 wires, 2 hot wires, each carrying 120 volts relative to neutral, and 1 neutral wire.
And where do they connect first on the house? The meter, right?
Right onto your power meter. That box, usually on an outside wall, maybe with spinning dials or a digital display.
The thing the utility reads.
Exactly. It's essentially the cash register for your electricity use. It measures how much energy flows into your home. And increasingly, with smart meters, it can also measure energy flowing out if you have solar, for example.
So that's how they bill you.
That's how they bill you. It also lets the utility monitor things and in some cases remotely connect or disconnect power. But yeah, definitely don't mess with it. It's dangerous and it's utility property.
Good advice. Okay, so from the meter, the wires go through the wall, and then where?
They enter the heart of your home's electrical system, the electrical service panel.
The breaker box. usually in the basement or garage.
Yeah.
That gray metal box on the wall.
That's the one. I like your analogy earlier. It's like the main highway interchange for all the electricity in your house. Power comes from the meter right into this box.
And the first thing it hits inside is the big switch at the top.
The main breaker, correct. It's the master switch for your whole house. All the power coming in has to pass through this single point, and its most critical job is safety.
How so?
If there's a massive surge of power coming from the utility or a really serious fault somewhere in your system, this main breaker is designed to shut off all the electricity to the entire house instantly. Protects everything downstream.
Okay, a big safety net. Once it's past the main breaker, where does the power go inside the panel?
It connects to what are called hot bus bars. Our sources describe these as sturdy metal strips or bars inside the panel. The incoming hot service wires energize these bus bars with that 120 to 140 volt power.
And the individual circuit breakers clip onto these bars.
Exactly. This is where that main flow of power gets divided up. The individual circuit breakers, or fuses in much older panels, physically latch onto these hot bus bars, drawing power from them. Each breaker then starts a separate path, a branch circuit, going out to different parts of your house.
So one breaker might feed the kitchen outlets, another the bedroom lights, and so on.
Precisely. And the primary job of those individual breakers or fuses is safety for their specific circuits.
Protecting just that one branch.
Right. If too much current tries to flow through that particular circuit, maybe you plugged in too many high-power appliances, or there's a short circuit somewhere, that specific breaker detects the overload or fault, and it trips. It breaks the electrical connection just for that circuit.
It's like a mini emergency shutoff for just that zone.
That's a good way to put it. By stopping the flow, it prevents the wires in that specific circuit from overheating. Overheated wires are bad news. They can melt insulation, cause sparks, potentially start a fire. So these breakers are absolutely critical fire prevention devices.
Okay, so power's generated, transmitted, distributed, metered, brought into the panel, split up by breakers. Now, how does it actually make my lamp turn on? Let's get inside the walls. Part 4. Powering your stuff.
All right. From each of those circuit breakers in the panel, wires head out into your home. These are the branch circuits we mentioned. The electricity travels primarily along the hot wire.
Usually the black insulated wire, right?
Typically, yes. This hot wire runs from the breaker, hidden inside your walls and ceilings, connecting to switches, outlets, and light fixtures. It's basically delivering the power to the point where you want to use it.
So when I flip a light switch on,
You're completing the circuit. You close a switch, which creates a path allowing electricity to flow from that hot wire through the switch into the light bulb, making it light up. Turning the switch off opens that path again, stopping the flow. Same idea when you plug something in and turn it on.
but electricity needs a round trip, doesn't it? It has to go back somewhere.
Absolutely. You need a complete loop. That's the job of the neutral wire. Our sources say this one is usually insulated and white. After the electricity has done its work lighting the bulb or running your appliance, the neutral wire provides the return path. It carries the, let's say, used current back towards the service panel, completing that electrical loop.
And back in the panel, all those white neutral wires connect together.
They connect to a neutral bus bar. And sources explain this neutral bus bar is connected back to the incoming neutral service wire, and also, crucially, it's bonded, connected to the ground system.
Ah, grounding. Okay, this sounds important. There's usually a third wire involved too.
Yes, absolutely essential in modern wiring, the grounding wire. This is often bare copper or insulated in green. This wire runs alongside the hot and neutral wires in most circuits. It needs to be connected to the metal boxes that house outlets and switches, to the metal casings of appliances, and most importantly, it needs a solid physical connection to the earth itself outside your home.
How do they connect it to the earth?
Usually via a thick copper wire clamped tightly to a metal cold water pipe entering your house, if it's metal all the way out, or, more commonly now, connected to a long copper-clad metal rod driven deep into the ground near your service panel or meter. It's called the grounding electrode.
Okay, but why? What does this grounding wire actually do? It doesn't normally carry electricity, right?
Correct. Under normal conditions, no current flows through the ground wire. Its job is purely safety. It provides a dedicated, very low-resistance escape path for electricity if something goes wrong.
Like what kind of wrong?
Like a fault. Say, the hot wire inside your metal toaster somehow comes loose and touches the metal casing. Without grounding, that whole toaster body could become energized at 120 volts. If you then touch the toaster while maybe also touching a grounded faucet,
Oh, no.
electricity sees you as a path to ground. That's how you get a serious, potentially fatal shock.
Yikes. So the ground wire prevents that.
Yeah. Yes, because the ground wire is also connected to that toaster casing and provides a much, much easier path for that fault current to flow directly back to the panel and then safely to the earth. This huge rush of current on the ground path will usually cause the circuit breaker to trip almost instantly, cutting off the power. It diverts the danger away from you. It's a critical layer of protection.
Wow. Okay, grounding is definitely not optional.
Yeah.
Now, speaking of safety devices, you mentioned fuses versus circuit breakers earlier. Let's clarify that.
Sure. Older homes, maybe pre-1960s or so, often have fuse panels. Inside, you'll find round, screw-in fuses. When a circuit is overloaded, a thin metal strip inside the fuse melts, it blows, and that breaks the circuit.
And you've got to replace it.
You have to unscrew the blown fuse and screw in a new one at the exact same amperage rating. Our sources really stress this. Never put in a higher amp fuse just because the old one keeps blowing. That's incredibly dangerous. The fuse is protecting the wiring. A bigger fuse lets the wires overheat, creating a major fire hazard.
Got it. So stick to the right size. And newer homes use breakers.
Right. Circuit breakers are mechanical switches. If there's an overload or a short circuit, an internal mechanism trips the switch, usually moving the handle to a middle position or sometimes fully off.
And you can just flip it back on.
Well, first you need to find and fix the reason it tripped, unplug the appliance that caused the overload, or have an electrician check for a short. Once the problem is resolved, you reset the breaker by pushing it fully to the off position, then back to on. They're reusable, which is convenient, but their main job, like fuses, is safety, preventing fires.
Okay. Safety extends to the outlets themselves too, you said.
Oh yeah, lots of evolution there. Our sources note that even back in the 1920s, we started seeing polarized outlets, the ones with one slot noticeably wider than the other.
Why the different sizes?
It ensures plugs designed with a wider neutral prong can only be inserted one way. This helps maintain the correct polarity, keeping the hot side of the circuit connected to the switch inside the appliance, which is generally safer.
Makes sense. And then came the third hole.
The grounding hole. Modern homes require grounded outlets, that round or sometimes U-shaped hole below the two slots. This is where the grounding pin on appliance cords connects, ensuring that vital safety ground path we just talked about is actually completed all the way to the appliance.
Crucial. And there's another type, especially important for kids.
Yes. Tamper-resistant receptacles, or TRRs. These have become standard requirement in new home construction since the 2008 National Electrical Code. They look almost identical to regular outlets, but inside there are little spring-loaded shutters blocking the slots.
Shutters?
Yeah. They only open when pressure is applied evenly to both slots simultaneously, like when you insert a proper two-pronged plug. This genius design prevents a child from sticking something conductive, like a paperclip or a key, into just one of the slots and getting a terrible shock or burn. Sources say these TRRs save multiple young lives every single year.
That's fantastic. A simple design change with a huge impact. And one more really critical safety device, especially near water.
Absolutely vital. Ground fault circuit interrupters, or GFCIs. You'll find these special outlets. They usually have test and reset buttons on them in places like kitchens, near the sink, bathrooms, garages, unfinished basements, crawl spaces, and all outdoor outlets. Anywhere electricity and water could potentially meet.
Which is a really bad mix. How do GFCIs work?
They are incredibly sensitive monitors. They constantly measure the amount of electrical current flowing out on the hot wire and compare it to the amount flowing back on the neutral wire. In a normal, healthy circuit, these two amounts should be exactly equal.
Okay.
But if even a tiny amount of current, we're talking as little as 5 milliamps, which is way too small to trip a regular circuit breaker, starts leaking out of the circuit, maybe it's finding a path through water or worse, through a person. The GFCI detects that tiny imbalance, and then it trips, cutting off the power almost instantly. Our sources say they can react in milliseconds, literally faster than a heartbeat, much faster than your nervous system can react to the shock.
Wow. So if my plugged-in hairdryer accidentally falls into a sink full of water while my hand is in there.
The GFCI should trip before you receive a lethal shock. It shuts off the power that quickly. It's a lifesaver. That's why it's so important to test them regularly.
How do you test them?
Just press the test button on the outlet, the power should click off. Then press the reset button to restore power. Doing that monthly ensures they're functioning correctly. It's a simple check that could literally save someone's life.
Definitely worth doing. Now, our sources also flag some older wiring types to be aware of. knob and tube.
Right. Knob and tube wiring was common in homes built roughly before the 1940s or 50s. You can sometimes spot it in unfinished basements or attics, individual wires supported by porcelain knobs and running through porcelain tubes where they pass through wood joists.
Is it dangerous?
It can be. It wasn't designed for the heavy electrical loads of modern homes. It lacks a safety ground wire, and the insulation can become brittle over time. A big hazard is if insulation has been blown in over it in attics, preventing heat from dissipating. Or if it's been improperly spliced into over the years. It definitely warrants inspection by a qualified electrician if you have it.
Okay. And there was another one mentioned, aluminum wiring.
Yes, used mainly in the 1960s and early 70s when copper prices were very high. The issue with aluminum is that it expands and contracts more than copper with temperature changes. Over time, connections at outlets, switches, and fixtures made with devices not specifically designed for aluminum can become loose.
And loose connections are bad.
Very bad. Loose connections create high resistance, which generates heat. This can lead to overheating, arcing, melting of fixtures, and is a significant fire risk. If your home was built or rewired during that era, our sources strongly recommend having an electrician check if you have aluminum wiring and if the connections are safe or need remediation.
Really important safety checks. Okay, one more common item. Extension cords. Everyone uses them. Any key tips from the sources?
Big ones. First and foremost, extension cords are for temporary use only. They are not a substitute for permanent wiring.
Right, don't wire your house with extension cords.
Please don't. Also, make sure the cord is rated properly for the power demands of whatever you're plugging into it. Using an underrated cord can cause it to overheat. And use cords rated for outdoor use. Only indoor cords aren't built to withstand moisture or temperature extremes.
Good point. What about running them places?
Never run them through walls, ceilings, doorways, or under rugs or carpets. This is a major fire hazard. It traps heat, and you can damage the cord without realizing it. Don't pinch them with furniture, and never nail or staple them down.
Keep them visible and untangled.
Exactly. Inspect them regularly for any signs of damage, cracked insulation, frayed wires, loose plugs. If it's damaged, discard it. And always look for a certification mark from a recognized safety testing lab like UL or ETL. Just a few simple rules can prevent a lot of problems.
Excellent advice. Okay, so we've followed the electrons all the way from the power plant to the outlet, covering safety along the way. But none of this just happens automatically. There are people and complex systems managing this whole thing constantly.
Absolutely. Let's zoom back out just a bit for part 5. Balancing the grid. Keeping this whole enormous network running smoothly involves thousands of people and incredibly sophisticated real-time systems and the fundamental challenge, day in, day out, second by second.
Balancing supply and demand.
Constantly matching electricity supply to electricity demand, yeah.
Okay.
In real time.
Second by second. That sounds incredibly stressful.
It is. Think about it. Demand is always changing. People turn lights on and off, factories start machines, AC units cycle, businesses open and close. At the same time, supply can fluctuate too. Maybe a cloud covers a big solar farm, the wind suddenly drops, or a large power plant unexpectedly trips offline.
Okay, if they get out of balance.
Bad things happen. The frequency of the grid, think of it as the heartbeat, usually 60 hertz in North America, has to be kept incredibly stable. If supply doesn't match demand, that frequency wavers. Too much demand can lead to voltage drops, brownouts, or even uncontrolled cascading blackouts. Too much supply can also cause problems. It's a constant tightrope walk.
So who's walking the tightrope? Who manages this?
There are specific organizations called balancing authorities. In many parts of North America, these are large entities known as independent system operators, ISOs, or regional transmission organizations, RTOs. Our sources kind of compare them to air traffic controllers, but for the flow of electricity. They monitor grid conditions across huge geographic areas constantly.
So they see everything happening.
They have a wide view, yes. They see the demand forecast, they see how much generation is available, they monitor the flows on the transmission lines, and if they see demand starting to climb higher than supply, or vice versa, they have to react instantly.
How do they react? What can they do?
They have several tools. They can signal power plants, especially those quick start peaking plants we talked about, to ramp up or down their output. They manage the flow of power between different regions, buying or selling electricity as needed. In really tight situations, they might have to initiate demand response programs, asking large customers to temporarily reduce their usage, Or, as a last resort, implement controlled, rotating outages to prevent a much larger grid collapse.
Wow, it really is like the world's most intense game of operational Jenga
Yeah.
running 24/7.
That's not a bad analogy. And to make sure everyone involved, the power plants, the transmission owners are operating reliably and playing by the rules, there are oversight bodies, like the North American Electric Reliability Corporation, NERC. They develop and enforce mandatory reliability standards for the entire bulk power system.
So there are rules and referees, too.
Absolutely. And increasingly, technology is playing a bigger role in managing all this complexity.
The smart grid.
Exactly. The smart grid isn't one single thing. It's more about integrating modern digital communication, sensors, automation, and advanced analytics into the traditional electrical grid infrastructure.
What's the benefit of making the grid smarter?
It makes it more resilient, more efficient, and gives operators better visibility and control. For example, smart sensors can detect outages or voltage problems much faster, sometimes even pinpointing the location automatically, which speeds up repairs. Advanced controls can help optimize power flow, potentially reducing energy losses. Utilities can manage voltage more precisely.
And this extends into our homes as well. You mentioned smart meters earlier.
Yes, smart meters provide much more detailed usage data back to the utility and often to the customer, too. And they enable two-way communication. This allows for things like demand response programs we touched on.
Where the utility can ask you to use less power.
Right. Sometimes it's a voluntary request with an incentive. Other times, if you enroll in certain programs, the utility might be able to communicate directly with your smart thermostat, or maybe even smart appliances like your water heater or pool pump, to slightly adjust their settings or cycle them briefly during critical peak demand periods. Always with your prior agreement, of course. It helps shave off that peak load across thousands of homes.
Fascinating. So my thermostat could be helping balance the entire grid someday. Which seems like a good lead-in to our final section, Part 6, looking at the challenges and the future.
Yeah, the grid is definitely facing some major challenges right now. A big one is simply age. A lot of the transmission lines, substations, and distribution equipment were built 40, 50, even 60 years ago. It's aging infrastructure that needs significant investment for upgrades and replacement just to keep things running reliably.
And building new stuff is hard, right?
Oop.
Especially big transmission lines.
Incredibly difficult. Getting permits and approvals to build new high-voltage transmission lines can take a decade or more. You have to deal with routing issues, acquiring land rights across multiple properties and jurisdictions, environmental reviews, local opposition. It's a huge hurdle, often called siting and permitting.
Which is a problem if we need new lines for renewables.
Exactly. That's another major challenge. Integrating large amounts of renewable energy like wind and solar. It's essential for decarbonizing the power sector and meeting climate goals, which is great. But these resources are often located in remote areas, windy plains, sunny deserts, far from the cities where most people live. So you need new long-distance transmission capacity to bring that clean power to the load centers.
And you still have the intermittency issue. Sun doesn't always shine, wind doesn't always blow.
Correct. That variability remains a core challenge for grid operators trying to guarantee power 24/7. How do you keep the system stable when a huge chunk of your supply can ramp up or down quickly based on the weather?
Storage is the answer again.
Energy storage, particularly grid-scale batteries, is seen as absolutely critical. Sources emphasize that battery costs are coming down and performance is improving. They provide that needed flexibility, storing excess renewable energy when it's abundant and dispatching it when renewables aren't producing or when demand is high. They can also help stabilize grid frequency and voltage very quickly.
Okay. What about the changes happening closer to home? The DERs, the rooftop solar.
That trend towards more distributed generation power being produced right where it's used or nearby is another big shift. Rooftop solar, home batteries, even electric vehicles that can potentially send power back to the grid, vehicle to grid or V2G. This requires pretty significant upgrades to the local distribution grid.
Because it wasn't built for power flowing backwards from houses.
Exactly. The traditional distribution system was designed for one-way power flow from the substation down to the customers. Making it capable of handling significant two-way flows reliably and safely requires smarter controls, more robust infrastructure, and new operational approaches. The future vision really involves us, the consumers, becoming much more active participants in grid reliability.
How would that work? My house helping the grid.
Through those smart devices we talked about, thermostats, water heaters, but also potentially through your home battery system or your EV charger. There's this concept emerging called virtual power plants, or VPPs.
Virtual power plants.
Yeah. Imagine software aggregating thousands of homes with batteries or smart thermostats or controllable EV chargers. The VPP operator can then manage these distributed resources collectively, bidding their aggregated capacity into energy markets or offering grid services like frequency regulation or reducing demand during peaks, just like a traditional power plant could.
So my home battery could get paid for helping stabilize the grid.
That's the idea. Regulatory changes are starting to enable this. Sources mention FERC Order 2222 in the U.S., which aims to allow these aggregations of DRs to participate more easily in wholesale electricity markets. It's a move towards a more interactive, participatory grid.
That's pretty wild to think about. Any other big future challenges?
Well, a constant and growing concern is protecting this increasingly complex and digitalized grid infrastructure from threats. That includes physical security threats like protecting substations from vandalism or attack, and also major cybersecurity threats against the control systems that operate the grid. Keeping the grid secure is paramount.
Wow. Okay. We have covered a lot of ground today. It really has been a journey.
It really has.
From these immense power plants, using everything from nuclear fission to sunlight, sending that energy across maybe hundreds of miles on those giant transmission towers, stepping the voltage down at substations and bringing it through our neighborhoods on local lines.
Right to your meter keeping track, then into your service panel where breakers safely split it up, out through the wires hidden in your walls, the hot and the neutral, doing their dance to power everything we rely on.
And all underpinned by that critical safety net of grounding.
Yeah.
It's quite something.
And remembering that behind that entire seamless process are thousands of people and incredibly sophisticated technology working nonstop 24/7 just to keep supply and demand perfectly balanced so that when you perform that simplest action, just flipping a switch, the lights come on.
It truly is a marvel of engineering, something most of us, myself included, take completely for granted. Understanding a bit about your home system is obviously important for safety, like knowing how to reset a breaker or test a GFCI.
Definitely.
But looking ahead, it seems the way our homes connect to and interact with that huge grid is set to become much more dynamic, much more active.
That certainly seems to be the direction things are heading. So maybe the next time you flick on that light or plug in your phone, just take half a second. Think about that hidden complexity, the incredible journey those electrons just took, and the vast, constantly humming machine that made it all possible.
And maybe ponder how your own home, with a smart thermostat or maybe a future EV in the garage, might soon be playing a small but active part in keeping that whole incredible machine humming along.
And that wraps up today's episode of Everyday Explained. We love making sense of the world around you 5 days a week. If you enjoyed today's deep dive, consider subscribing so you don't miss out on our next discovery. I'm Chris, and I'll catch you in the next one.